Let's welcome Dr. Lisa Randall.
Good afternoon. It's a pleasure to be here, and I'm going to tell you about how physics helps us see things that we think of as invisible. And I'm going to focus on two topics that are dear to my heart and my research. I'm going to talk about extra dimensions, which you heard a little bit about earlier, and also dark matter. So the universe certainly extends beyond what we see. But it's amazing that people think that things don't exist when they don't see them. But we know that we have very limited vision. We basically see only with visible wavelengths, and when we talk about what we see in our daily lives, we see directly. But there are many reasons that we would miss things by just focusing on that. One is that things could emit light, but they could be outside visible wavelengths. And of course, we have tools and techniques. You've heard about infrared telescopes earlier, to look at wavelengths that we don't directly see. Could be that there's stuff there that actually doesn't emit light. We're going to hear about dark matter, which is an example of that. It could be that things are just too small to see. We just don't resolve it. It could be that extra dimensions of space even fall into that category. And some stuff just might not be accessible. Maybe there's stuff in the way, or we're just not looking in the right direction. But I think the worst reason and the worst excuse would be we just didn't think to look. It was within our realms, and we just didn't think about it. So what I do as a model builder is we try to think about what we could look for. What are those things that might be accessible to what we're observing today that we would otherwise miss? And this is a really great era for discovery. Two major discoveries, of course, were gravity waves, which you heard about earlier, which are just an amazing new way to view the universe. And the Large Hadron Collider at CERN discovered the Higgs boson a little bit before that, which gave us some insight into how particles acquire their masses. And I'll tell you a little bit about how we want to go beyond what the CERN and the Large Hadron Collider have already done. So let me tell you very briefly about extra dimensions of space. So we're all familiar with 3 dimensions of space. That would be left, right, forward, backward, up, down. Again, that's what we see in our daily lives, what we experience, what even the laws of physics seem to indicate. However, I'm going to try to explain that there could be, we don't yet know, but there could be dimensions of space beyond those that we directly observe. So how should we think about that? Well, the basic lesson is going to be just don't try to picture it, because if you try to picture it, you'll get into trouble. That's not to say there haven't been great simulations of projections, et cetera. But let's think about ways that we do try to picture it, and then we'll talk about other ways to think about it. So one of the ways is slices. So let's go down a dimension, and let's imagine for a moment that we were 2-dimensional creatures in a 3-dimensional world. How would we observe 3-dimensional world? There's a lovely book called Flatland, which actually talked about that. And you would basically see slices. You could see things that came through. For example, you could imagine that a sphere came through what was known as Flatland, the 2-dimensional universe. And what would you see if you lived on that plane that is Flatland? Well, you would see a series of disks that grew in size and then decreased in size as it passed through. So at any given moment, you wouldn't see the full 3-dimensional object, but you would be able to put it together and realize something 3-dimensional had been there. And in the same way, the fact that we live in 3 dimensions, if some 4-dimensional hypersphere came through, what would we see? We would see a series of spheres that increased in size and then decreased in size. And again, we would never see the 4-dimensional sphere in its entirety, but we'd be able to put it together. Another way that we have for looking at thinking about dimensions, again, by reducing it to lower numbers, and again, let's think about 3-dimensional objects, but seen in a 2-dimensional way, is projections. So here's an example of a projection that tells you why a single projection can be very misleading. Those of you who know about the joke, the usual projection that you have to make a rabbit, understand why this is a joke. But basically, having a single projection doesn't give you all the three-dimensional information. But if you put a bunch of projections together, like you do in a CAT scan, for example, you could reconstruct the three-dimensional information. So again, you're not seeing the three-dimensional thing at one time, but you're putting it together. And in the same way, we might hope to put together information about higher dimensions. There's also other ideas like holograms. Something you will do in physics is you just don't think about some of the dimensions when there's a symmetry, and you can treat them all together, and that does allow you to draw pictures. You can average, like for example, if a dimension is too small to see, you don't detect it, so it might as well not be there. So you're just seeing some sort of average effect. But I'd say the real lesson is we really want math and words when we think about extra dimensions, not necessarily pictures, which can be deceptive. What about extra dimensions in physics? Well, Theodor Kaluza produced an extra dimension of space, the idea of an extra dimension in space, in 1919, very soon after Einstein had been working on relativity. There was basically no reason they can't be there. And in fact, we know that Einstein's equations of gravity work in any number of dimensions. String theory, which I'm not going to talk about, but you heard mention of quantum gravity, suggests that there are at least 6 more. But I'm going to leave the existence and number for experiment, but let's speculate about what the consequences could be. Now, it's interesting because Einstein actually refereed Kaluza's paper, and he delayed publication for 2 years because he said, if there are these extra dimensions, they're clearly different, we don't observe them, and what makes them different? And the idea that was proposed by Klein was that extra dimensions can be really tiny. They can be curled up to a tiny size. And so in this case, you have to imagine that you're thinking about the entire universe. So you're thinking about a dimension of the entire universe. So here we have a 2-dimensional world. So it's many lower dimensions, so it's a 2-dimensional world. And you can imagine that one of those dimensions is curled up, and then you think of it as a 1-dimensional universe, even though the universe is fundamentally 2-dimensional. If you can't detect that other dimension, you don't know it's there. So in 1999, my collaborator Raman Sundram and I found that there was another way to hide dimensions, and it was based on an important ingredient in string theory whose importance was relatively recently recognized, called brains. Again, you heard about that a little bit earlier in Kip's beautiful talk. And those are membrane-like objects in higher dimensional space. And it turns out they play an essential role in string theory. Now, why could they be important for physics? Well, many reasons. But one of the reasons is that we could actually live in what's called a brain world, a higher dimensional world in which everything we know, everything we think of as the 3-dimensional world, is actually stuck on a brain. Now, here I have a picture of a 2-dimensional brain world with illustrating that there's forces like gravity and people and maybe even suns and planets stuck on that 3-dimensional world, here a 2-dimensional world. But the thing that's not stuck is gravity. So gravity explores what's known as the bulk, the higher dimensional space, whereas maybe other forces and even us and our universe that we know is stuck on a 3-dimensional brain. So again, the universe would be fundamentally higher dimensional, but it would help explain why we only see lower dimensions of space. With brains, we found many interesting consequences if you have extra dimensions in brains. There could be a new way to hide dimensions. Instead of just curling them up, you could actually have geometry so warped, and again, you heard about warping earlier, but so warped that you don't see that extra dimension. There could be a new concept of our place in the universe. Maybe we live in a localized region that looks like 3 dimensions, even though fundamentally it's higher dimensional. And what's interesting from the point of view of possibly detecting consequences of this extra dimension is there's a new way to explain the weakness of gravity. And the reason that's possibly detectable ties back to the Large Hadron Collider, which I mentioned in my first or second slide. And that has to do with something that's known in physics as the hierarchy problem. The question is, why is gravity so weak compared to the other elementary fundamental forces? Now, gravity might not seem weak when you're climbing up a mountain, for example, but if you think about it, a magnet can take on the entire Earth. A magnet can pick up a paperclip, even though the entire Earth is acting on it. And that's because fundamentally the strength of gravity is much weaker. And from the point of view of elementary particles, gravity is orders of magnitude more weak than other forces. And it might not sound like such a big issue. You'd say, well, maybe it's just weaker. But it turns out that if you put together quantum mechanics and in what we know is field theory, when we think about particle physics, it turns out that it almost looks inconsistent. You have to kind of fudge the theory or introduce some really arbitrary cancellation that no one really believes exists. So the question is, why is it that gravity is so weak, given that the theory almost predicts that it shouldn't be? And the answer can naturally be found in a multiverse where you have two brains. There's other proposed explanations. That's what the Large Hadron Collider is in fact looking for. What is it that underlies the Standard Model, underlies the Higgs boson that's been discovered? But one of the possibilities is that there could be a warped extra dimension of space. And in this picture, what you see are there are two brains. One is the brain world that I told you about earlier. That's where we're living. Another one here is labeled the gravity brain, and that's where gravity is concentrated in some sense. Gravity is stronger if you're on that brain, and it actually decreases exponentially weakly as you get to the second brain. Now, that's not just an arbitrary assumption. It turned out that was actually a solution to Einstein's equations that we found when we put in two flat brains in this extra dimensional geometry. So it turns out it's very warped, and if you look at the strength of gravity, it's as if it decreases exponentially as you go from the gravity brain to the weak brain, which means we can very naturally explain why gravity is so weak in our universe. It's exponentially suppressed here in the region that we live. Are there experimental tests? After all, this sounds like a pretty crazy idea. And the interesting thing is that the scenario is testable. Because of the connection to masses, which is connected to the Higgs boson, and the weakness of gravity relative to other known forces, collider experiments, such as those at the Large Hadron Collider, have about the right energy to search for the consequences of this theory. So right now, this is happening at the Large Hadron Collider in CERN, where they're reaching energies higher than have been achieved before. But to be honest, they haven't found it. What they're looking for are Kaluza-Klein particles, particles that travel in extra dimensions and have extra momentum associated with those extra dimensions. So they look to us like heavy particles, and they have about the right mass that we should expect to see them in around there. What would happen is you collide together particles you know about, but then they produce particles through the Kaluza-Klein particle that we can detect. And this is a very interesting aspect of this theory. A lot of times when people talk about extra dimensions of space, you talk about Kaluza-Klein particles that just disappear into the extra dimensions. In this particular warped geometry, it turns out the interaction itself is warped, so that the particles actually would decay in the detector. So it's not yet ruled out, even those explaining the weakness of gravity. It could be that these particles are a little bit too heavy to be found at the Large Hadron Collider, and there's some reasons to think that's the case. This is why I and some of my colleagues, many of my colleagues, are very enthusiastic about the idea of what has been known as the Great Collider, a Chinese large collider. We're really grateful and excited that you're taking this idea seriously, because without achieving higher energies, we won't know what's going on at these short distance scales. If the Large Hadron Collider is the highest energy we achieve, that means that that's basically the shortest distance we're going to directly explore. And there's a world of possibility for what can occur if we can achieve higher energy. And that might be the goal of a collider here in the future, which we find very promising. So that's all I'm going to say about extra dimensions for now. I was asked to talk about both extra dimensions and dark matter. So I'm going to spend the rest of the talk talking about another thing that's hidden from us, but it's not quite as hidden in some senses. Because in this case, we actually have detected the gravitational influence. And it's known as dark matter. And what you see on the slide is what's sometimes known as the cosmic pie. That tells us that that little white wedge, about 5% of the energy of the universe, is stuff that we know about, the stuff that we're familiar with, stuff made up of atoms. The rest of it is in some sense, dark. There's a component called dark matter, which is stuff that is matter. It interacts with gravity like matter. But as far as we know, it doesn't interact with light. There's also dark energy, which is stuff not even carried by matter, which is spread throughout the universe and is related to the acceleration of the expansion of the universe. Now, the question we have is, I'm going to try to explain to you very briefly why we are so confident that dark matter exists. But as a researcher, we're trying to figure out what it could be. After all, it's not made up the same stuff that our matter is made up of, that we know about. So again, it's matter that interacts via gravity like matter, but it's very little, if other, interactions that we know about. And certainly very little standard model interactions. That's to say, very little interactions with atoms that we're aware of, aside from gravity. In some sense, it's not really surprising it should exist. I mean, why should the matter that we're made up of be everything? And in fact, there could be billions of dark matter particles that pass through you every second, but you don't detect it because, as we said, gravity is such a weak force. Gravity is so weak that even with all these dark matter particles right here, we are unaware of their existence. Now, just to clarify something, we call it dark matter, but it's not dark. My jacket is dark. It absorbs light. It should be called transparent matter. It's matter that light just passes through. Nonetheless, it was critical to giving shape to the universe that we know. There's 5 times the energy in dark matter than ordinary matter, and that was critical to structures like our galaxy forming. So why am I so confident that dark matter exists? So how do we see this stuff that isn't dark? Well, clearly, all we detect so far is its gravitational influence, but we've detected it in many different ways. Those include galactic rotation curves. That was, in fact, one of the ways dark matter was first discovered. Dark matter, in our galaxy, stars orbit, and they go so quickly that if there weren't additional matter, they would fly out of the galaxy. In other words, the gravitational force that attracts these stars that are rotating consists of ordinary matter plus something else, and that something else is dark matter. We also see in galaxy clusters, which are groups of galaxies, galaxies themselves move faster than can be accounted for by the visible matter. There's something called gravitational lensing, which again you heard about briefly earlier today, which is another way that you can see evidence of dark matter, because dark matter actually influences the path of light. There's a number of ways. One of the ones that I find most compelling is something called the bullet cluster, which again, clusters are groups of galaxies that are gravitationally bound together. And if you look at the bullet cluster, it very clearly has the structure of clusters that merged. But when they merged, something very interesting happened. The stuff that we know interacts, like gas, which is illustrated in pink in the picture, stays in the center, whereas other stuff, which is the dark matter and is not interacting, has gone through, and that's why you see the blue on the outside. So it acts exactly as you would expect matter to do. That doesn't have interactions. It just passes through and collects together as dark matter. But maybe one of the most important of the consequences of dark matter, as I said earlier, is the existence of galaxies in the lifetime of the universe. And also to have a galaxy on the scale of the Milky Way. If it had just been ordinary matter, radiation would have washed it out. So dark matter, despite the fact that a lot of people are unaware of it, was critical to the formation of our galaxy. So it's not speculation. We know dark matter exists. We don't see it with our eyes, but we observe its gravitational influences. But we don't yet know where it is, what it is, and that's where research comes in. Because we have to think about candidates for what it can be if we're going to figure out how to find it. So I'm going to tell you about one piece of research which is quite speculative, and has some very interesting speculative consequences. Again, I'm not going to tell you that this is definitely correct. I'm telling you that this is a theory, and I'll tell you how we can test the idea. So we propose that there's a distinct type of dark matter. Most of the dark matter is non-interacting, but some of the dark matter has interactions. And I'll argue that not only is this testable, but it might have even affected the solar system, triggering comet strikes, one of which might have killed the dinosaurs. Okay, so what's our basic insight? The basic insight is that why should normal matter be the only one that's so special? After all, dark matter isn't necessarily just one type of particle. After all, our universe consists of, the stuff that we see consists of many different types of particles with many different types of interactions. Maybe some of the dark matter, not necessarily all of it, but some of the dark matter is charged. And just the way dark matter doesn't experience our light, maybe our stuff doesn't experience a light that dark matter sees, which I'm calling dark light. So in other words, dark matter has its own interactions with its own type of light that we do not observe directly. In that case, it could have some remarkable consequences. It turns out that the Milky Way that you saw pictures of earlier, at Bark's talk, I believe, the Milky Way is formed because ordinary matter radiates. So dark matter sticks around in a more or less spherical halo, but ordinary matter can radiate, and because of that, it can collapse. If dark matter also has its own form of light, it too can radiate. And then what you might have is a dark matter disk inside the disk that we see of the Milky Way. And again, we don't know this exists, but it's something that would have observable consequences because it would affect the motion of stars. So in particular, if you look at stars that go up and down through the Milky Way plane, they would see a different gravitational potential. And what's so exciting is that the Gaia satellite, launched by the European Space Agency, is actually measuring the motion, the position, and velocities of stars in the Milky Way. And by doing that, they can actually test for the consequences of this theory, and that's going on as we speak. But let me just finish off the talk by telling you about the more crazy potential consequence of this theory, which may or may not turn out to be right, but does have some testable consequence. So we think about the solar system. We know about the solar system, of course, having now 8 planets, but it also has stuff that moves around, such as asteroids and comets. Well, the Kuiper belt is more or less the source of short period comets whose period are less than 200 years. But there's also something known as the Oort cloud, which is thousands of times farther away from the sun than the Earth. And because of that, the objects in the Oort cloud, which are the source of long period comets with period greater than 200 years, those things are only weakly attracted to the sun. That means if you give them a small kick of some sort, that the stuff could be kicked out of the solar system or be more likely to come towards Earth. And that's important because we know that stuff does hit the Earth, and we know that the last major mass extinction was caused by one such object. So our idea is that we can have this, as the sun orbits around the galaxy. The sun is the whole solar system. It orbits around the galaxy about every 240, 250 million years. As it does so, it bobs up and down slightly and crosses the Milky Way plane on a periodic basis. Now, if it crosses the Milky Way plane and there's this dense disk of dark matter, that means there would be extra tidal forces acting on everything, including the weakly bound stuff of the Oort cloud. So the idea is that maybe when the solar system is passing through the dark matter disk, you're more likely to eject things from the Oort cloud, and hence more likely to have objects that come hurtling towards the Earth. So what we would look for would be periodic large impacts that could come from this particular source, and that would be caused by a dark matter disk that had very particular properties, which are things that we can look for. So let me just finish off the connection to why I think it could have anything to do with extinctions. And that's because, I'm sorry, this slide got very badly cut off. It was supposed to be fixed. Anyway, the last major mass extinction, there have been 5 major mass extinctions in the Phanerozoic eon. Major mass extinctions are where half to two-thirds of the species on the planet disappear. That is to say, they not only die off, but their descendants die off. So there really is a major resetting for life on Earth. And the last one occurred 66 million years ago in something called the KPG mass extinction. And it's a very fascinating science story that brings together many different fields of science. How we determined that that last major mass extinction was in fact caused by a big object. And by big, I mean 10 to 15 kilometers in size, the size of a major city. I don't know how the size of Beijing compares, but it's a major city that comes hurtling towards Earth at about 30 kilometers a second. So basically, when that happened, many disasters happened. And it created the conditions for a major mass extinction, where not only the dinosaurs, but two-thirds of the species on the planet disappeared. In fact, that's very important to us, because it's what allowed for the development of mammals from being these small species that buried underground to being the stuff that, in some ways, dominates the surface of the Earth. So in many ways, our existence is owed to this big rock that, in fact, hit the Earth. The question is, what did it come from? Well, our idea is that maybe this rock was one of the, and we can fit and show you that it could have been one of the periodic comet strikes, and that's actually what created that mass extinction. And I'm just going to show just a couple of photographs, just because you really can go around and see on the surface of the Earth the evidence of this extinction, which I don't have time to tell you about, but I was fortunate to do in Spain and also in Denmark, where there's a layer of rock that corresponds to where that object hit, and it corresponds in time. So you see white rock below with lots of life, and gray rock above where the life disappeared. It's a very distinct layer, and it's all around the globe. So it was clearly some event that affected the entire globe. And it's also really beautiful places that you get to go to when you see that. So I don't know if this dark disk idea is right, and the search for it is ongoing as we speak, as is the search for extra dimensions. But I do know there's a lot more about the amazing connections in the universe, and ultimately to life, that we have to find. And the only way to do it is to have these major projects where we go and look for these things, and to try to tie them together to theoretical ideas where we can explore. And my publishers from Cheers are here, so I will tell you that if you want to learn more, you can check these 3 books, which are also published in Chinese. Thank you very much.